Hello everyone. Today we'd like to present our service learning project with the topic distillation and its application. The objective of this service learning project is to enhance the knowledge dissemination related to the field of chemical engineering and engage with the community. The scopes of service learning are educate the public and students on distillation processes and applications, promote community engagement using digital platforms like YouTube, and develop video production and demos. Here are some general principles of distillation. First, the basic of distillation. It is a separation process based on volatility differences in liquid mixtures. The driving force of this process is differences in boiling points and vapor pressures. It consists of three key components. They are the boiler to provide heat, trays of packing to increase contact area, and condenser to cool vapor. Next, the vapor-liquid equilibrium reactions, also known as VLE reactions. There are three types of diagrams which are PXY, PXY, and YX diagram. The rules law describe vapor pressure mole fraction relationship, PXY in ideal conditions, for example, benzene toluene mixtures with this equation, where Henry's law applicable to dilute non-ideal solutions with this equation.
Next, we'll cover distillation calculation and design. Firstly, we're focusing on the two main distillation design types, which are simple batch distillation and flash distillation. The slide shows the key general equations and example diagrams for both. In brief, simple batch distillation uses a fixed liquid mixture, while flash distillation involves a continuous feed. Now, let's discuss about the concept of relative volatility. Basically, it defines the separation efficiency based on weapon pressure, compositions, or K values between two volatile components in the mixture solution, as shown in the equation below. It helps indicate the feasibility and difficulties of separation, with highest values suggesting easier separation. Additionally, its values are influenced by temperature, pressure, and mixture composition. Next, the McCann-Gillen method is one of the main graphical techniques used to determine the theoretical stages of a distillation column. The key concepts include the enriching and stripping section, the feed quality line, reflux ratio, and the pinch point where theoretical stages become infinite, represent the minimum reflux ratio. The typical design trade-off of a distillation column involves finding a balance between the number of stages and the reflux ratio to ensure an efficient and feasible operation. The diagram below shows the general graph used for this method. Now let's move on to the types of distillation processes. In general, there are six main types, and we start with simple distillation first. This method usually separates liquid components with a boiling point difference of at least 25 degrees Celsius by heating the mixture, vaporizing the more volatile component, and collecting it while the less volatile components remain. It's ideal for mixture with large boiling point differences. Next, fractional distillation is another distillation method that separates miscible liquid based on boiling point differences. The lower boiling point components vaporize and condense first. As the weapon rises through the fractionating column, an example shown in the right circle in the right-hand side diagram, it then becomes enriched in volatile components. Repeated condensation and vaporizations at different columns level allow for efficient separation and distillate collection. Next, moving on to steam distillation. This method is used to extract temperature-sensitive and volatile compounds. The process involves passing hot steam through the mixture to vaporize the desired compounds at lower temperatures, then condensing and collecting the vaporized components. This process prevents the decomposition of heat-sensitive substances and is commonly used for purifying essential oils and aromatic compounds.
Vacuum distillation is a technique to separate liquids with very high boiling points by lowering this pressure. This reduces the boiling point, making separation energy efficient and preventing heat-sensitive substances from decomposing. It is widely used for purifying chemicals safely and effectively. Azeotropic distillation is used to separate mixtures by adding external components. Azeotrophs have constant boiling point and can't be separated by simple distillations. The added component changes the interactions between mixtures components, allowing effective separations. Extractive distillation is a process for separating components with the similar boiling points using a non-volatile solvent. This solvent alters the relative volatility of one key component, making separation easier during distillations. Unlike azeotropic distillation, it doesn't break azeotrope but focuses on the changing of volatility for effective separations. Now I'll briefly explain the differences between the azeotropic and extractive distillations. Azeotropic distillation is used to separate azeotropic mixtures where components have the same boiling point and similar vapor-liquid compositions. The main goal is to break the azeotropes by adding the entrainers that forms new azeotrope with the distinct boiling points. This method is specifically designed for the mixtures that can't be separated by simple distillations. And on the other hand, extractive distillations aim at separating mixtures with close boiling points, even it is don't form azeotropes. Here, the entrainers doesn't create an azeotrope but alters the relative volatility of one component. It is versatile and can handle a broader range of mixtures. Both techniques are vital in chemical industries for achieving high purity separation efficiently.
Distillation is a separation process with numerous applications across various industries, and there are some key applications which are water purification, petroleum refining, essential oil extraction, wastewater treatment, ethanol water, mixture separation, and finally aromatic hydrocarbon separations. For the first application, which is water purification, the simple distillation is used to purify water through boiling, condensation, and collection process, and the contaminated water is heated to specific boiling point and evaporate to form steam vapor, leaving impurities, inorganic compounds, and large non-volatile organic molecules. And the steam is then cooled and condensed using condenser back into liquid, and which is purified water. For the second application, which is petroleum refining, and the fractional distillation is used to separate crude oil based on differences in boiling points. The crude oil is heated to a very high temperature, which is about 350 to 400 degrees Celsius, to vaporize the substance leaving heaviest compounds. The resulting vapor is then entered, separating column will rise and cool. The components with higher boiling points will condense at lower levels of towers, while the lighter fractions condense high ups. So this process produces various fractions of valuable products such as gasoline, kerosene, diesel, and heavier oils, which can be further processed into final products. The steam distillation method is used to extract essential oils from plants. So the steam passes through plant sample, and the essential oils evaporate with the sample. So the mixture of steam and essential oil vapor is condensed into liquid by cooling. And the essential oils, which are hydrophobic and can be separated from water to be collected. And this method is particularly useful for extracting heat-sensitive compounds, as the steam's temperature is lower than the direct boiling point of the oils, preventing degradation.
Hello everyone. So just now my team actually talk about the three applications of the water distillation process. So I'm going to take over for the last three. So first of all, it's actually the wastewater treatment. Actually, in this wastewater treatment, we're actually using the volatile organic compounds we wish to remove from the wastewater itself. So by applying the vacuum distillation, it actually helps us to separate and condense and also vaporize the volatile organic compounds, oil or other contaminants that is much more lower than the boiling point provided by lowering it due to the operational pressure itself. And also another application is using the separation of ethanol water mixture, where we're actually using the isentropic distillation to actually produce high purity of ethanol that is used in fuel and also pharmaceutical applications itself by adding entrants such as benzene to actually break the isentrop, and it will form a new isentrop with the water only. And to further add on, the last application is actually a separation of aromatic hydrocarbon mixtures, where we actually use extractive distillation to actually separate one of the methods to separate the aromatic hydrocarbons. And at the end of the day, it helps us to enhance the efficiency of separation by forming a vapor liquid equilibrium to effective recovery of high purity of aromatic carbons compounds itself. And in the short conclusion, right, the distillation is actually a fundamental process present in our daily life to applications and separate different type of materials into their respective pure components in the industry. And throughout this service learning, we hope that we achieve our main objective by sharing our knowledge and research on the learnings we gain from the separation process course. And I hope you enjoyed this video, and thank you so much for listening.